Welcome and hello. This is a video exercise in WRIMS. And in this exercise, we're going to do an example of linear programming, specifically least cost routing. We're going to be using the WRIMS linear programming solver engine to do a couple things. First, we're going to solve the LP problem, and also we're going to get some exposure to the Russell plus programming language and its syntax. All right, so what I have on the screen here is the WRIMS user interface. We're going to get to that in just a moment, but before we do, I want to introduce the linear programming problem that we're going to solve using WRIMS, and then solve it and explain the answer. Then we're going to write some code to basically perform the same calculations. All right, so here is a video that I created some 15 plus years ago about linear programming. I will leave a link to this video in the description of this video. Okay, it's on the same channel in my operations research playlist called Linear Programming 4. And the question is, we need to find the minimum shipping cost, and it's actually formulated as a multiple choice problem. So I'm going to bring up some slides just to summarize this. What we have is, this is America with 3 different factories in blue and 5 different warehouses in red. And what we want to do is ship product cases from the factory to the warehouse. In the next slide here, I just identified the different cities. If you're not familiar with the United States, you can do the same sort of problem in any country with any set of cities. But anyway, so we have factories in Nashville, DC, and Detroit, and then we have warehouses in Dallas, LA, Chicago, New York, and Atlanta. So we want to move the product from the blue dots, the supply, the factory, to the red dot, which is the demand, or the warehouse. All right, what I've done in this slide here is identified the amount of supply that each factory can provide. So again, we have 3 factories, Detroit, DC, and Nashville, labeled S1, 2, and 3, S for supply. And as you can see, we have 12, 7, and 15 is the supply. So you could think this is the number of 100,000 cases in a month, or whatever the time period is, doesn't matter. So 1.2 would, or 12 right here would actually be 1.2 million, 7 would be 700,000 cases, and 115 would be 1.5 million cases. In the next slide, we have the demands for the 5 different warehouses, Chicago, LA, New York, Atlanta, and then behind the table here is Dallas. So those are D1 through 5, and then these are the demands for that particular product. So 5 here, for instance, would be 500,000, 400,000, 400,000, 1.1 million, and 800,000. All right, on this slide here, we identify the decision variables. So there's actually going to be 15 decision variables. That means there is 15 different paths of 3 factories times 5 warehouses. So the first subscript here represents the factory, S, and then the second number here in the subscript represents the warehouse, which is D, or the demand. So this first row here represents the number of cases that's shipped from factory 1 to warehouses 1, 2, 3, 4, and 5. And then the second row here, X sub 2 comma D, would be the amount of cases shipped from factory 2 to warehouses 1, 2, 3, 4, and 5. And then from factory 3 is X sub 3 comma D, where D is the warehouse 1 through 5. Below that, we have the C transpose vector, which is the transport costs, which is the cost to transport a case from factory S to warehouse D. So C11 right here is the cost associated with transporting a case from factory 1 to warehouse 1. C12 is the cost of transferring a case from factory 1 to warehouse 2, factory 1, warehouse 3, 4, and 5. So right here, for instance, C sub 2 comma 4 would be the cost of transporting a case from factory 2 to warehouse 4. So those numbers and subscripts are represented earlier. So C sub 2, for instance, that would be supply 2 is DC, and then the warehouse 4 is Chicago. This is the cost right here, and then this is the actual decision variable X sub 2 comma 4. Okay. And then the objective function is here at the bottom. What we want to do is minimize the costs, so subject to all the constraints. We'll get to the constraints in the next slide. Here is the actual costs. So in the red numbers here, you're seeing the actual number. So we're going to be using this in our objective function value. And in the next slide, here it is. This is our constraints. So we have our supply constraints right here. This basically means that the factory cannot generate or fabricate more than 1.2 million, 700,000, and 1.5 million cases of product. And then the demand constraints are down below. This basically is a minimum where we have to have at least these different amount of cases delivered to the warehouse. And of course, we have the non-negativity constraints for all of our 15 decision variables, which is all 3 factories delivered to each of our 5 different warehouses for supply and demand. Okay. Now, we could solve this by hand, and that's what I do in the video right here. I go into detail about adding slack variables or surplus variables and artificial variables, and ultimately solving what is called phase 1 of a simplex tableau, where we just solve the algorithm in order to find an initial feasible solution. We're not doing that. All the solvers I've come across, whether it's Microsoft Excel or, of course, WRIMS, which is what we're going to be using, already have that built in. So we don't have to suffer from a headache just doing that. We have to know the RESL plus programming language and syntax, and we need to be able to understand the formula and formulate it in a standardized format like what we're seeing here. All right, the last slide here is the solution. So the decision variables right here for the optimal solution are shown in blue, and it's 0, 4, 4, 4, 0, all the way down to 6, 7. So x sub 1, 1 means 0, x sub 1, 2 is 4, and that means we're going to have 4 cases delivered from factory 1 to warehouse 2, and then another 4 cases delivered from factory 1 to warehouse 3 and warehouse 4, and so on. Again, here are the same costs, and if we actually do the sum product, that C transpose X comes out to $2,035,000. All right, so these are the numbers, these blue decision variables, and this final objective function value is what we're hoping to obtain after we put all of this into a linear programming engine such as WRIMS. All right, so let's put the slides away. And then I'm going to open up not this web page, but the other link in the description is going to take you to this page right here. It's CalSim documentation. I'm going to actually download an example, simple linear programming problem. So if you go ahead and click CalSim 3 documentation, and then on the left, there is a session 1 intro. Go ahead and click that. And then over in this table here for linear programming, the second row is CalSim 3, and then over here in this hands-on column, simple LP, go ahead and click that link. It's going to open up a new page, and then here is a zip file which you want to download. So just click on this download link and then wait for that to download. All right. So it downloaded onto my desktop right here. I'm going to find a location on my computer. I want to save that file. Let's go ahead and open it up. Okay, simple LP. Here are the files. Just going to go right click and copy, minimize, and then right click and paste this into a location on my computer that I can reference it. So this is going to be the project directory. You see we have the launch file right here. And then here's the RESL file, which is where we're going to modify the code. All right, so I'm going to go back to RIMS, new project. And then for general project, that's good. I'll click next. For a project name, I'm just going to call this E1, least cost routing for exercise 1. And then the path right here, this needs to be the directory of the project that .launch file is located in. So I'm just going to come up here and then copy the path and then head back. Okay, I updated the directory. This is my directory. I'll click finish. And boom, E1 least cost routing. Over here in the Project Explorer, I'm going to click the triangle to expand. And now we see our initial files. Now this particular simple LP problem has a linear programming problem associated with it that's a little bit less complex. But we're going to go ahead and open up this .WRESL file in a text editor and then go ahead and make some edits. So here is the project directory. Here is that simple LP problem.WRESL. I'm just going to go ahead and right click, open that up in my text editor. Here it is right here. Here is the existing problem, so you can check that out if you want. It's also covered in my lesson 2 for RIMS lesson 2. And this is exercise 1, though. We're going to level up and do a more difficult problem. So I'm just going to go ahead and delete everything, and then we're just going to slowly paste in some code. So we're going to start with a giant comment that basically describes everything. So boom, here it is. This is a multi-line comment. Everything I just pasted in, these 20 rows or lines of code, is actually commented out, so it won't be read in by the interpreter. What we're trying to do here is minimize Z. So this is that C transpose X function where we have the cost coefficient of 0.9 times the decision variable x11, 1.05, decision variable is x12, all the way to the cost of 0.85 times the decision variable x35. The demand constraints right here basically say that there needs to be at least this quantity of cases delivered to these separate cities. And then below that, we have the supply constraints, which basically means that each factory cannot generate more than 1.2 million, 700,000, and 1.5 million for Detroit, Washington, and DC, respectively. Lastly, we have the non-negativity constraints where each decision variable x sub sd must be at least 0. All right. So this is all comment. It's just sort of a pseudocode for us to remember what we're working with here, and that these are the variables we're going to be using. Okay, I'm going to go ahead and scroll down a little bit, give myself some more rows. And then what I've pasted in here is the sequence command. We only have one sequence. I'll call it cycle one, or sorry, it's named model LCR, and it's going to be order number 1. So this is the one and only sequence that we're running. Below that, I'm going to paste in some code to run the model. Model LCR is just short for least cost routing. And if I scroll down a little bit, right here, what I'm doing is I'm defining the 15 different decision variables. So this is how you define a continuous decision variable. It's not an fixed to be integer. There's no minimum or maximum bound per se. I mean, we will add the constraints later, but for the most part, the name is x11. So this value right here will be, I believe it's part B in the resulting DSS file, and then the kind here will be in part C of the DSS file, the file path. And then the units I just called cases, so it's sort of generic. But anyway, yeah, these are the 15 decision variables. Next, I'm going to be pasting in the demand constraints right here for the 5 different cities. The command we want to use here in the Russell code is goal. Now, goal to me sort of sounds like this is an objective function, but goal is actually a constraint. In this case, it's a hard constraint where the left-hand side has to be greater than or equal to the 5, for instance, 5 cases, or more specifically, 500,000 cases, but we can add those 5 extra zeros a little bit later. And then here's the demand for Los Angeles, Dallas, Chicago, and New York. The Russell Plus User's Manual mentions that in LP that the greater than symbol also assumes that it's greater than or equals symbol. So I'm just going to go ahead and work with that syntax so that this value can equal 5. The same way this sum can equal 4, and this sum can equal 4, and so on. Just like a demand constraint, we're also going to have a hard constraint for the supply, which means Detroit, Washington, D.C., and Nashville cannot supply more than the allotted quantities specified. And then further down below that, I'm going to paste in the non-negativity constraints. So nothing too exciting here. I'm naming these constraints NN and then the variable name for non-negativity. And then those values have to all be either equal to or greater than 0. And then the last line of code I want to paste in is, of course, our objective function value. So that'll go below all of the constraints. It's going to be called objective right here. And it's going to have, I'm just going to call it cost because that helps me remember that we want to minimize this objective function. In the first argument, we have the decision variable and then comma and then the cost coefficient. Now, as I understand it, WRIMS will always try to maximize unless there's some way to minimize, and I don't know how to do it yet. But what I did was I just set the cost to a negative value. That way we could still use a maximization function just by flipping the sign of the cost. So what we want to do is minimize the cost or maximize the negative cost is ultimately what we're doing here. So this is it. This is what I'm going to save the .wresl file to do. I'm going to scroll up to the top and then just save. And I move that out of the way. Let's go back to our WRIMS now. And that file is saved. It's part of the project already, and it will be referenced. So when I go right click on the project name and then come down here to run as, run configuration. And then in the left panel here, if I click on demo_LP, we see that the main Russell file is the one right here, which is what we were editing. And then some of the auxiliary files where it writes out our decision variables are down below. All the other data, I'm just going to leave default and then click on run down here in the bottom right and then wait for that to run. Okay, so that finished up. It maybe took 5-10 seconds, not too bad. Let's go ahead and take a look at the results. Let's open up this simple LP underscore DV.DSS file. This should have our decision variables. I've got DSS view open here. I'm going to open up that DSS file by navigating to it. Here is the project directory, and then here is that simple LP underscore DV.DSS file. Okay, I need to go to view and then refresh. All right, so this variable 1 and variable 2 were left over from the previous file. We don't need that. What we have now is the 15 different paths, each representing one of the decision variables of the number of cases to transport from factory S to warehouse D. If I click on the table button, we can see what those results are. 04440, that should look familiar because if I bring up the optimal values, we have 0, 4, 4, 4, and 0. Those are the quantities shipping out of factory 1. Out of factory 2 should be 50002. So what we have here is 50002. And then out of factory 3, it's 00007 and 6, which according to the results I have here is 00076. So this 6, for instance, is factory 3 transporting to warehouse 5. If I go back, we have factory 3 is Nashville, and it's transferring to New York, which is warehouse 5, D5. I've also noticed that factory, so 12, 7, and 15, those are the total fabrication capacity of our 3 factories. But then if I scroll forward to the results, we have 12, 7, and 13, which means we have an extra 2 units or 200,000 cases that can be fabricated out of that Nashville factory. So we actually have a slack variable right here, which means we just probably the cost shipping out of Nashville are too high, and we can look at the cost coefficients right here and determine that is true. All right, so those are our decision variables right here. I'm going to go ahead and go back to RIMS. And then the objective function value should be right here in note cbc underscore obj.log. So if I click that, it's asking for me to refresh. That's fine. I'll just go right click and refresh. And then boom, we have 20.35, which if we multiply it by 1 times 10 to the 5th, that would give us our $2,035,000, which is the cost to transport those cases from the factories to the warehouses. All right, well, that is it for this exercise. What we did was we looked at a problem in linear programming, specifically a least cost routing problem, which I have a video of in the description. Then we solved this problem and determined what the decision variables were, what the constraints were, what the objective function was, and ultimately what the solution was. After that, we took our WRESL file and then formulated the pseudocode and ultimately the code by defining the variables and then the constraints, the objective function values with the proper syntax in this Russell Plus programming language, and then ran it through the RIMS solver to give us a solution.